Welcome to Target IS. I am Om Prakash Rajput, and today we are continuing with the basics of electromagnetic field theory. And today we will cover the topics differential length, area, and volume, and use of del operator. Then we will find divergence and curl and Laplacian of scalars and vectors. So let us start with differential length, area, and volume. So why this differential length, area, and volume will be required? We will be dealing with integration of a line, surface, and volume. So we will be requiring differential length vector, differential area vector, and differential volume for a typical surface. So that's why we will start doing this. What is differential length? So if I consider the rectangular coordinate system here, and I want to find the differential length in this coordinate system. So if I want to move from P point to Q point, then I will go in the direction like this, then this, and this. I can travel from here to here and here also. So I will reach the same point. And from moving from, suppose if this point is P and this point is Q, let us take this point as R, this point as S, this point as T, and this point as U. So if I moving from P to R, this distance will be dx, and I'm moving in the x direction, this will be dx ax cap. If I'm moving from R to S, then RS can be written as, I'm moving in the y direction, so it is dy, and in the y direction it will be ay cap. And then I'm moving from S to Q, so SQ will be dz az cap. So I can simply say that PQ is dx ax cap plus dy ay cap plus dz az cap. So this is nothing but the differential vector. If I go from like P to T, then it will be dy ay cap, then T to U, then it will be dz az cap, and then U to Q, then it will be dx ax cap. So it is similar to PQ only. If I move from P to Q in the other direction also, it will come as dx ax cap plus dy ay cap plus dz az cap. So in rectangular coordinate system, the differential length vector is given by dx ax cap plus dy ay cap plus dz az cap. In every problem, ये कोई ज़रूरी नहीं कि अगर एक प्रॉब्लम दी हुई है आपको तो सारे चीज़ें यूज़ होगी, डी एक्स ए एक्स कैप भी यूज़ हो, डी वाई ए वाई कैप भी यूज़ हो, और डी जेड ए जेड कैप भी यूज़ हो। डिपेंड करता है कि आप कहाँ से कहाँ ट्रैवल कर रहे हैं। सपोज इफ़ यू आर मूविंग फ्रॉम पी पॉइंट टू यू, देन the requirement will be of dy ay cap and dz az cap only. There will be no requirement of dx ax cap. Okay, so this is the differential length in the rectangular coordinate system. Now if I talk about cylindrical coordinate system, then the differential length, if it will be same like if I take this point as P and this point as Q, this point as Q, then the differential length will be this d rho, and this differential length is nothing but this rho d phi, and this is dz. So we can write directly the differential length vector will be, if I'm moving in the rho direction, it will be d rho a rho cap. If I'm moving in the phi direction, so rho will be constant and it will be rho d phi a phi cap. As it is a length, so rho is multiplied with the d phi, and in the z direction it will be dz az cap. So this is the differential length in cylindrical coordinate system. And if I talk about the spherical coordinate system, so here you can see, if I make this as so, in the spherical coordinate system, if I consider this differential element, and if I'm moving from this point, suppose to this point, then I will cover this distance. Here theta is varying, so r will be multiplied, so it is r d theta. And then I will go here, this will be same as the rho d phi in the cylindrical coordinate system. So rho was r sine theta, so here it will be r sine theta d phi. And then I will change the radius, so it will be same as the dr. So the differential length in spherical coordinate system can be written as dr ar cap plus r d theta a theta cap plus r sine theta d phi a phi cap. This is the differential length in the spherical coordinate system. Now we will see differential surface, differential area. So if you want to talk about differential area, then suppose if I am considering this surface, so on this surface the variables are dz and dy, dz and dy. If I consider this surface, then the variables are dx and dy, dx and dy. Now if I consider this surface, the variables are dx and dz. You can see here also dz dy for this surface, dx dy for upper surface, and dx dz for this surface. And the unit vector for this surface vector is perpendicular to the surface we have taken. So if I take this surface, the unit vector which is perpendicular to this surface will be in the direction of z, and for this surface will be in the direction of y, and for this surface will be in the direction of ax. So if I write the surface differential surface vector ds vector, so it will be dx dy if I consider this surface, so and the unit vector is in the direction of z. And if I consider this surface, so it will be dy dz ay, sorry, not ay, ax cap. I'm considering this surface, and the other one will be dx dz ay cap. So this is the surface area vector, or differential surface area vector we can say, for the rectangular coordinate system. And same thing with that is this, that we don't need to use all these things like dx dy for every problem. We will require dx dy or dy dz. We will require, if I take a surface like this surface, so I will require only dy dz dy dz ax cap for this surface. In a certain problem, if I take this surface, so I will be requiring dy dz ax cap, that is this thing only I will require for this surface. So depending on the problem, we will see what we require from the differential surface area vector. So now we can also find the differential volume for this, and volume will be scalar, not vector. So in this all the parameters will be varying. So this will be dx dy dz. This is differential volume for the rectangular coordinate system. Now for the cylindrical coordinate system, if I want to find out the differential surface vector, it can be same written as for cylindrical coordinate system. So you can see here, if I consider this area, then it will be dz d rho, and in the direction of a phi cap, unit vector in the direction of a phi cap. So dz d rho a phi cap. If I consider the other surface like this, so it will be dz rho d phi A phi cap will be arrow cap will be the unit vector. So dz d phi, and I will write rho here, and it will be arrow cap. So rho dz d phi arrow cap. And if I consider the upper surface, if I consider the upper surface, then it will be rho d phi d rho. So I can write it as rho d rho d phi, and unit vector is in the direction of az cap. So you can see that whatever the parameters we are taking in differential, the unit vector is the other one which is remaining. So if I take d rho and d phi, then the unit vector will be az. If I take dz d rho dz or phi, unit vector in the direction of rho direction. And if I take z and rho, so dz d rho and unit vector in the direction of a phi. So this is the differential surface vector in cylindrical coordinate system. Dz d rho a phi cap, rho dz d phi a rho cap, and plus rho d phi d rho az cap. We can also find out the differential volume for this also. So differential volume will be rho d rho d phi dz. This is the differential volume for cylindrical coordinate system. Now if I consider the spherical system, so spherical system, this is nothing but d theta, and this is dr, this is dr, and this is r sine theta d phi. This is d theta, but here r is constant, so r d theta, and this is r sine theta d phi. So we can write differential surface vector for this as, if I consider different surfaces like this pink one, then the variables are r d theta and dr, and unit vector will be in the direction of phi. So for this it will be r dr d theta a phi cap, plus if I consider some this like this gray surface, then the variables are r sine theta d phi, and this one is r d theta. So I can write r square sine theta, r square sine theta d theta d phi, and unit vector is in the direction of, unit vector is in the direction of ar cap, ar cap. And if I consider the yellow surface, then the variables are r sine theta d phi and dr. So I can write r sine theta dr d phi, and unit vector in the direction of the remaining parameter, that is a theta cap. This is differential surface vector for spherical coordinate system. I can also write the differential volume here. It will be multiplication of all the differential element, that is r sine theta d phi into dr into r d theta. So it can be written as r square sine theta dr d theta d phi. So this is differential volume for spherical coordinate system. Now let us see this problem. In this problem, calculate the work done, calculate the work required to move the cart along the path shown in the figure. Along the path shown in the figure against a force field F. F is given by 3xy ax cap, 4xy ay cap, and work done is given by delta W is equals to F dot integral, line integral of F dot dl. So here the path is shown like from we are moving a cart from point A to point B along this path. So we have to evaluate this integral here. that is line integral of f dot dl. So here we are moving from A to point B. So we can break this into two parts. First is here we can take this first one, and this is second part. Suppose this point is C. So first we will do the integral for A to C, then we will do from C to B. So first A to C. So A to C, suppose it is delta W 1 will be equals to integral of line, that is first part. Here I am considering the first part of f dot dl. So what is f here? Here f is same obviously. It will be 3xy ax plus 4xy ay cap dot a to c. A to c we are moving in the x direction. So the differential length will be dx ax cap. So differential length will be dx ax cap, and what are the values of dx? From this is 1 to 4. So we can put the limits of integration from 1 to 4. So if we solve this here, it will be 1 to 4 3 y ax cap dot dx ax cap. The other term, if I do the dot product, ax dot ay will become 0. So only the term remaining will be this. So ax dot ax will become 1. So only thing which is left is 3xy dx. And what you can see here is the y is not varying here. So y is constant. Y is constant for path 1. It is 1. So we can use the value of y as 1. So if I put y1 here, the remaining part will be 3x dx, 3x integration 1 to 4 dx. And if I solve this, I will get, if I solve this, I will get 45 by 2. So this is my delta W for first part. Now I will do for the second part, that is from C to B. That is from C to B. From C to B you can see that only y is varying. Only y is varying. And x is constant at value 4. So we can use value of x as 4, and the differential length here will be dy ay cap. Differential length here will be dy ay cap. So we can use this. So we will write it as, suppose the delta w2 is equals to integral. I will write the f equation 3xy ax cap plus 4xy ay cap, and the differential length here will be dy ay cap, and the limits of y are 1 to 2. So if I multiply dot product here, so ax dot ay will become 0, and only term remaining will be ay dot ay will become 1. So only term remaining will be 4xy dy, and in 4xy dy x value is 4. So 4 into 4 will become 16. So it will be 16y dy, and limits are 1 to 2. And if I solve this, I will get 24. So I will get 24. So the net work done net work done, that is delta W. I can write delta W1 plus delta W2. So delta W1 was 45 by 2 and delta W2 was 24, and if I solve this, it comes as 93 by 2, or we can write 46.5 joule. So this is the solution for this problem. This is how you can use differential length vector in different coordinate systems also, like in cylindrical and spherical also. Now we will move to our another topic, that is del operator. Del operator is a vector differential operator represented as delta and defined as del by del x ax cap plus del by del y ay cap plus del by del z az cap. So it is a differential vector del by del x ax cap plus del by del y az cap plus del by del z az cap. So it is an operator that operates on scalar or a vector. So if this operator operates on a scalar, then it is known as gradient of scalar. It is known as gradient of scalar. So we can define gradient of scalar as del dot v. So this is my scalar quantity v. So it will be del by del x of v ax cap plus del v by del y ay cap plus del v by del z az cap. Now this is in rectangular coordinate system. If I want to write this in cylindrical coordinate system, I can also do that. In cylindrical coordinate system, if I want to write this in cylindrical coordinate system, so del dot v in cylindrical coordinate system cylindrical coordinate system, it can be written as del v by del rho a rho cap plus del by del phi del v by del phi del v by del phi a phi cap and del v by del z a z cap. Now here we have seen that this is del rho, this is del z, but this is del phi is not length. Del rho and del z are length, but del phi is not a length. So we need to multiply this by length. So so we are using here 1 by rho, 1 by rho. Now I can write this in spherical coordinate system. So in spherical coordinate system, if I want to write del dot v, then it will be del v by del r ar cap plus del v by del theta a phi, sorry, del v by del theta a theta cap plus del v by del v by del phi a phi cap. Now here you can see that del phi and del theta are not lengths, so we need to make them as lengths. So we need to write here 1 by r, and here I have written 1 by rho. So rho in spherical coordinate system is r sine theta. So here this will be 1 by r sine theta del v by del phi. So this is gradient in spherical coordinate system. Now you can see the gradient of a scalar is a vector quantity. Gradient of a scalar is a vector quantity. This is a vector quantity. This is again a vector quantity. This is again a vector quantity, and this is also a vector quantity. So you can see that gradient of a scalar is a vector quantity. So what this gradient tells is, it tells the maximum rate of change of v. V is the scalar, maximum rate of change of v, and we it also says about the directions at in which the rate of change is happening in v. So gradient of a scalar field is maximum rate of change of v. Now we'll start another topic, that is divergence of a vector. So divergence of a vector, if we apply del operator, if we apply del operator on a vector, then it is divergence of the vector. So by divergence of a vector means total outward flux per unit volume is given by this divergence. So we will see that in a moment. What is that divergence? I will write divergence in three coordinate system. There is three formulas in different coordinate system we have learned. So in rectangular coordinate or rectangular system, del dot a vector is given by, suppose my a vector is ax cap plus ay cap plus az cap. So del dot a becomes, if I do dot product with the del operator, it will be del by del x of x component plus del by del y of y component plus del by del z of z component. This is divergence in rectangular coordinate system. Now if I write divergence in cylindrical coordinate system, so it will be, in cylindrical coordinate system, it will be del dot a vector. A vector will be having components in aero cap plus a phi cap plus az cap. So this is some different formula. I will write here del by del rho a rho plus del by del phi a phi. Here we know that it is not length, so 1 by rho plus del by del z of az. But here is something different. What is this different? We'll see. Here 1 by rho, and here also 1 by rho will come. So this is the formula in cylindrical coordinate system for the divergence. Now we will see in spherical coordinate system. If I consider spherical coordinate system, then what will be the formula for divergence? So if I consider a vector in spherical coordinate system, it will be ar cap plus a theta cap plus a phi cap. So divergence of a vector will be given by, in spherical coordinate system, del by del r ar. There is also one additional term, I'll write it later. Del by del theta of a theta. Here also one additional term, plus del by del phi of a phi. Here we know that it is not length, so here comes 1 by r sine theta. So what are the additional terms for the spherical coordinate system? Here it is 1 by r square, here also r square, and in this 1 by r sine theta, and here sine theta. So this is the formula. If I write it again in a correct way, so it will be like this: 1 by r square del by del r of r square ar plus 1 by r sine theta del by del theta of sine theta a theta plus 1 by r sine theta del by del phi of a phi. So this is the formula of divergence in spherical coordinate system. Now let us move to our next topic, that is divergence theorem. So divergence theorem states that for a closed surface, if I do surface integral for a closed surface for a vector, it will be equal to divergence of that vector over the volume of that closed surface, So this theorem can convert the surface integral into volume integral. We will use in electrostat and magnetostat as well, but mainly in electrostat, this theorem. So it states that closed surface integral of a vector will be equals to volume integral of divergence of that vector. So this is the divergence theorem. In other words, we can also say that divergence theorem states that total outward flux, that is A dot ds through a vector field A, vector field is A, through the closed surface which I am taking, through the closed surface, will be equal to volume integral of divergence of this field. So this is divergence theorem. Now we will see a numerical on this. So here it is a question. It is given that for a vector field, this is a vector field x y z square ax cap plus x y square z ay cap plus x square y z ay cap. Evaluate the surface integral for a unit cube defined by, this is how it is defined, 0 से 1, 0 से 1 y and 0 से 1 z. तीनों की लिमिट्स जो है वो 0 से 1 के बीच में, that is it is a unit cube. It is already mentioned in the question also. So we have to find the surface integral for this. So let us find. So this is my unit cube. We have to do surface integral for this, that is the given vector field over this closed surface. We are going to do A dot ds. So I will be doing surface integral for every surface. So as this cube has 6 surfaces, so for every surface we have to do surface integration. So let us see. if I talk about this surface, the behind one, here the value of x is 0. The value of x is 0. So the A field becomes 0 because in every component there is x. Similarly, in every component there is y and z also. So the surface integral for this surface will also become 0 because here the value of y is 0, and for this surface the value of z is 0. The value of z is 0, the below surface. So we have to calculate surface integration for three surfaces only which are remaining, and they are, so the three surfaces which have surface integration non-zero are this surface, the front one, this surface, the right one, and the upper surface. So this surface the value of x is 1. I can say this is a x equal to 1 surface. For this surface the value of y is 1, so I can say this as y equal to 1 surface. At this z equals to 1, as this is a unit cube, so the value of x, y and z will limit to 1. So at the boundaries their values are 1. So for x equal to 1 surface the value of x is given, and we know that for this surface the unit vector will be in the direction of x. So only ax component I will take from the a vector, that is x y square, x y square, sorry, not x y square, it is x y z square, and the value which are varying for x equal to 1 surface will be dy, the surface vector, that is dy dz. The surface vector for this surface will be dy dz, dy dz ax cap. So only ax component will be taken for the x equal to 1 surface. I will put x equal to 1 later, but I will write now. So now the value for the next surface, that is y equal to 1 surface. For y equal to 1 surface the uh, surface vector will be dy, dx dz ay cap. So I will take only ay component, and ay component is x y square z, and the surface vector is dx dx dy, and ay cap dot ay cap will become 1 plus, for this y equals to 1, for this x equals to 1. Now I will write for z equal to 1 surface. For that I will take z component because its surface vector will be az cap. So x square y z, and the surface vector will be dx dy az cap. So this is z equals to 1 surface. Now I will simplify it. So I will take double integral where the limits of the other values are from 0 to 1 as given in the question, and x will be put as 1, so it will be yz square dy dz plus, here y equals to 1, so it will be xz dx dy plus, here also the limits will be from 0 to 1 and 0 to 1. Here also I will take double integral, and here I will put z equals to 1, and the x square y z, and the limits are 0 to 1, 0 to 1 for dx dy. Z equals to 1 I have put it, so z will go. So this is, I have to solve this now. So if I solve this, it can be simply solved. Now simple integration dy, y dy integration will be y square by 2. So it will give me 1 by 2 into, for z square it will be z cube by 3. So it will be 1 by 3 plus, for x it will be x square by 2. So it will be 1 by 2 into, for z it will be, here there is a silly mistake. Here it is actually dz, because ay cap, this surface I am taking. So ay cap will be in there, and the variables are the surface vector, differential surface vector is dx, because x is changing and z is changing. So dx dz. So here also it will become dx dz. Now the z dz integration will be z square by 2, and it will give 1 by 2 plus, for this x cube by 3. So it will give 1 by 3, and for y it will be y square by 2. So it will give 1 by 2, and if I solve it completely, it will give me 7 by 12. So this is the surface integral, which is a dot ds, a dot ds. Now if I want to verify the divergence theorem for this question, if I want to verify the divergence theorem for this question, I will check that surface integral of a dot ds will be equal to del dot a over the volume integral or not. So I will first find del dot a. So del dot a will be del by del x of, as from the formula. Here I will write the ax component, that is x y z square plus plus the del by del y x y square z plus del by del z x square yz. So if I solve this, I will get, what I will get is, for the x I will get yz square plus, for this I will get 2x yz, 2x yz plus, for this x square y. This is del dot a, del dot a. Now I will take volume integral of this. Now I will take volume integral of this. So it will be yz square plus 2xyz plus x square y over the volume integral dx dy dz, and the limits for x, y and z are from 0 to 1. Limits for x, y and z are from 0 to 1. So I can simply solve this, and it will be, first I will solve for like z component. So it will become like like if I do the triple integral and I am doing the z component integration, so this will become yz cube by 3 plus 2xyz square by 2 plus x square yz, and the limits are 0 to 1. The remaining integrals remaining are dx dy, and now I will solve this. So it will become, if I put the value of z, so it will be like y z cube, z cube will become 1, so y by 3 plus, here 2 and 2 will get cancelled and remaining will be x y plus z will go and x square y will remain. Now I will do dx dy. So dx dy I will do now. So I will do integration with respect to y now. So it will be y square by 2. So it will become y square by 6 plus xy square by 2 plus x square y square by 2, and I will put the limits 0 to 1, and the remaining is dx. So now I will put the values. So it will be 1 by 6 plus, it will be 1 by 2, sorry, x will remain, x by 2 plus, and it will be x square by 2 and dx. Now I will solve for this. It will be x by 6 plus x square by 2 will come for this, so it becomes x square by 4 plus, here x cube by 3, and the values are 0 to 1. So if I solve this, it will be 1 by 6 plus 1 by 4 plus 1 by 3, and if I solve this, I will get 7 by 12. I will get 7 by 12. A little mistake here, let me rectify it. Here I will integrate, so it will become x cube by 3, so here it will be x cube by 6, and this is also 6, and now it will come as 7 by 12. So this is volume integral of divergence, it is 7 by 12, and I have found that surface integral was also 7 by 12. So hence the divergence theorem here is verified, as the volume integral of divergence and the closed surface integral is same. So hence the divergence theorem is verified here. So this is all for this video. We will meet in the next video and continue with the curl and Laplacian, and we will see few problems also on different things like divergence, curl,